For 2 years, the software industry has focused on building AI agents under the assumption that they can operate with autonomy. That assumption fractures the moment these models interact with live infrastructure. Last month, an autonomous agent built with industry-standard tools deleted 3,000 rows from a production database. The agent's code functioned as intended, and the model's reasoning was logically sound. However, the system lacked the context to recognize its own environment. It executed the deletion because it failed to track the state of its connection, incorrectly assuming it was still operating in a test sandbox. This schematic illustrates the standard workflow used by most developers today. A user prompt feeds into an LLM, which is then granted direct access to execute tools against a production database. Granting an LLM direct API access without a management layer creates an operational liability. LLMs excel at logical reasoning, but they struggle to maintain the temporal context of their environment. In the database failure, the agent lost the thread of its environmental state. It could not remember that it had moved from a safe environment to a live one. Multi-step workflows require stateful execution, a baseline where the system maintains a continuous record of its preceding actions and environmental status. Deploying a non-deterministic model into an environment that requires rigid state awareness leads to system breakdown. Note how the LLM remains isolated from the timeline of past events. It operates in a vacuum, unaware of the consequences or context of the steps it took moments before. Reliable production agents require a deterministic architecture built outside of the model to manage its actions. There is a common misconception that an agent's ability to call an API is the same thing as successfully completing a task. While an LLM can initiate an action, it often lacks the awareness to stop when it encounters an error. As we zoom into the tool execution node, we see the agent encounter a failed API endpoint. It receives an error bounce back and immediately attempts to resolve it by sending the exact same parameters again. This creates a repetitive cycle of identical failed requests. Standard agent designs often lack a retry budget, a hard-coded limit on how many times an operation can be attempted. These unmanaged loops consume cloud compute resources and can lock system processes indefinitely. Without these hard-coded limits, autonomous retry logic can inadvertently function as a self-inflicted denial-of-service attack. Connecting an agent to a vector database does not provide it with system memory. Vector databases allow for fast semantic retrieval of static data, but they don't track the agent's history. Effective memory requires more than retrieval. The system must understand what was done, why it was done, and which actions led to errors. To compensate for this lack of memory, many developers implement human-in-the-loop approval gates for critical actions. These approval gates often slow down the workflow until the human operators are buried under a cascade of tickets. This leads to severe alert fatigue. In many cases, engineers eventually disable these gates during testing or high-volume periods to clear the queue. This removal of safeguards is the specific point of failure that led to the database deletion incident mentioned earlier. Relying on human stamina to supervise machine speed operations creates an architectural vulnerability. A defensive build starts with the assumption that the raw output of an LLM cannot be trusted blindly. The first defensive layer is validation middleware. This sits between the reasoning engine and the execution tools. Here, the validation middleware severs the direct connection between the LLM and tools, forcing requests through a deterministic choke point. It enforces rate limits and scope boundaries, blocking a request to a production table and routing it to a safe failure bin. By forcing the system to fail safely outside of the model's control, we neutralize the risk of unmanaged autonomy. To address the lack of temporal memory, we move from continuous execution to discrete managed states. We use state checkpointing to record the agent's exact status at fixed intervals. As the workflow progresses, the system saves a snapshot of its progress into a lightweight cache. When an error occurs on step 4, the system does not enter a retry loop. Instead, the timeline snaps back to the saved snapshot at step 3. By providing a mechanism to return to a known good state, checkpointing creates a functional history for the system. In these architectures, memory is the ability to navigate that history and undo a failure. Even with guardrails and rollbacks, a single reasoning engine remains a single point of failure. The final layer is adversarial agency, a two-agent peer review protocol. The LLM node splits into two parallel agents. A secondary model audits the execution plan proposed by the first. Agent A proposes a path, Agent B evaluates it. Execution proceeds to the middleware only when both agents merge at a verified consensus gate. Running Agent B on a different temperature setting ensures variance in reasoning, helping to catch blind spots that a single model might overlook. While this doubles the computational cost, it is significantly less expensive than recovering from a major production failure. When we review this defensive architecture in its entirety, we see a system designed for control. This is the complete agent observability stack. Two adversarial agents route their decisions through validation middleware, while every step is recorded by a state checkpoint cache. This stack provides explainability, the structural ability to prove why an agent took a specific action. It also ensures reversibility, the architectural guarantee that any action can be rolled back. Deterministic observability is now the technical requirement for deploying AI agents into production environments. AI agents are becoming a standard part of software infrastructure, but their deployment now requires engineered control. Today's engineers are shifting towards structural controls, building resilient guardrails to manage these raw model capabilities with absolute precision. If you cannot explain your agent's reasoning or roll back its failures, you are not building an autonomous asset. You are deploying a liability.